Welcome to course UEC 001. On previous module, we were talking about operational amplifier where we have seen several aspects. Now, in this module, we will discuss in detail on the two terms CMRR and Slew Rate, which we were discussed in short on the previous module. The meaning of CMRR is common mode rejection ratio. Common mode rejection ratio. So in order to understand the function of this parameter common mode rejection ratio, let us understand first uh, the term differential and common mode operation of differential and common mode operation of an op-amp. So with this article we can derive mathematical relationship for common mode rejection ratio, and we will see how to solve this particular term common mode rejection ratio. In fact, there is a certain error, so let's remove it. Okay, so let's start with the differential mode operation. So as the name suggests, differential mode operation means we require one op-amp and we have to apply signal to both the apply the signal to both the input, and the signal should be of different value. The signal should be of different value. Suppose this is V in 1, V in 2. So over here we will have VD, differential input signal over here, and my output is V0. So in this situation, the differential input signal, which is my VD, this should be equals to V in 1 minus V in 2. VD will be equals to V in 1 minus V in 2. And I'm assuming that in this situation my gain is differential voltage gain, and which is termed as AD. So here AD is my differential voltage gain, which is concerned in relation to the differential operation of the operational amplifier. For common mode operation, with the name one can easily understand the term. That means a common signal has to be applied to the both inputs. So for that, what I am doing, I am making a short circuit across the both and giving a common signal. I am giving a common signal over here, my inverting terminal, non-inverting terminal. These are my two terminals over here, V1 and V2. And I am representing my common signal by C. So here VC is the common signal. VC is the common signal. And I'm assuming that in this situation, if in this situation. If signal correspond to inverting terminal is V in 1 and signal corresponding to V in 2, that means my signal Vc will be average value of these two. So it will be average value of V in 1 plus V in 2. This is my common mode signal Vc. At the same time, I am saying that the gain, voltage gain, voltage gain in common mode configuration will be equal to ACM. So I am using the notation ACM, where my ACM is representing common mode voltage gain. ACM is my common mode voltage gain. Therefore, my output voltage, therefore, my output voltage V naught will be termed as, it is AD, that is my differential voltage gain, multiplied by differential input voltage VD plus common mode gain ACM multiplied by a common mode signal Vc. So my overall output voltage, by considering these two terms, my overall output voltage by considering these two terms together will be equals to V naught equals to AD into VD plus ACM into VC, where VC is my common mode signal. The case 1, if opposite polarity inputs, if opposite polarity inputs are applied. Let us check the performance if opposite polarity inputs are applied. So for that, let us take V in 1 equals to Vs and V in 2 equals to minus Vs, because we are saying that we are having the opposite polarity signal. So V in 1 equals to Vs and V in 2 equals to minus times of Vs. So what is my differential gain? We have seen from the formula Vd equals to V in 1 minus V in 2. So obviously this will be equal to what? This will be equals to Vs minus times of Vs, that means twice Vs. So my Vd will be equals to, for this particular case, differential input voltage Vd will be equals to twice Vs when different or opposite polarity, rather than different, opposite polarity inputs have been applied. For the same situation, let us find the value of common mode signal Vc. So my Vc will be equals to average value of both inputs 1 by 2 Vs plus and minus Vs. So you can see that this becomes 0. That means in the same situation, the value of common mode signal Vc will be equals to 0 when opposite polarity signal is applied. Okay, so let us determine the output voltage for this case. Let us determine the output voltage V naught for this case. This will be equals to AD multiplied by twice Vs plus ACM multiplied by 0. That means my output voltage is AD into twice Vs. So what we can understand, I will have at the output my signal which is twice multiplied by differential gain. That means common mode signal will not be there. So what is the benefit of this case? You can check if opposite polarity signal is applied, so there is a chance that noise can be appear to both the terminals. So in this situation, noise will be completely attenuated and at the output only desirable part will be available. Now let us consider the second case. Let us consider the second case if same polarity inputs are applied. Consider the second case when same polarity inputs applied to the output. Now I am considering V in 1 will be equals to V in 2 and this will be equals to suppose Vs. Interesting part is you can check now I am using a common signal having a same polarity being applied to both the inputs. And now let us examine the first case Vd. So my Vd will be equals to V in 1 minus V in 2, that means equals to Vs minus Vs. So this will be equals to 0. That means my differential input voltage is 0 if same polarity signal is applied. And the case for common mode signal Vc, this will be equals to 1 by 2 of V in 1 plus V in 2, and this will be equals to 1 by 2 of Vs plus Vs. So ultimately equals to 1 by 2 multiplied by twice Vs, or ultimately my Vc will be equals to Vs only. So let us calculate the value of output voltage for this category. Output voltage is now AD, differential voltage gain, multiplied by 0 plus common mode gain ACM multiplied by Vs, or effectively my output voltage V0 becomes ACM into Vs. So I am having very interesting result over here. For the first case, if I am applying signal of opposite polarity, then we have seen that such in such situation noise is completely removed and whatever be the desired signal will be available at the output with its amplified version. However, in the second case, if same polarity signal is applied over here, then the common mode signal will appear across the output, whereas the desired signal will be completely attenuated. Now, in order to understand the meaning of common mode rejection ratio, we have to determine these two components first, AD and ACM. So first, which we have discussed, AD, that is my differential voltage gain, and ACM, common mode voltage gain. If these two parameters are known to us, then we can easily calculate the common mode rejection ratio, or this is nothing but the ability of operation amplifier to reject the common mode signal or noise. So if we are for the measurement of uh, Let us take first part, the differential input voltage first. So for that, take uh, the value of V in 1 equals to 0.5 volt and V in 2 equals to minus zero point 0.5. I can check what is my differential voltage. VD will be equals to V in 1 minus V in 2, so it will be equals to zero point 0.5 minus zero point 0.5, that means equals to 1 volt. Okay, and at the same time I am calculating VC, which is 1 by 2 V in 1 plus V in 2, and this is equals to 1 by 2.5 plus minus zero point 0.5, which is ultimately 0 volt. Therefore, you can check my output voltage AD into 1 plus ACM into 0. Therefore, output voltage V naught equals to AD. So by setting V in 1 equals to zero point 0.5 volt, V in 2 equals to minus zero point 0.5 volt, I can easily calculate the differential voltage gain of the operation amplifier V naught. Okay, now let us check the second case, measurement of ACM. Measurement of common mode gain ACM. So for this, for the measurement of ACM, let us have value V in 1 equals to V in 2 equals to 1, when both equals to 1. So by this you can check value of VD equals to 0 volts. Now I am not writing in detail. By using the above formula you can easily calculate, and common mode signal VC will be equals to 1 by 2 multiplied by 2, so will be equals to 1. Therefore, again the output voltage V naught equals to AD into 0 plus ACM into 1, or ultimately my output voltage is ACM. So by these simple steps we can easily find the value of AD, that is my differential voltage gain, and value of ACM, common mode voltage gain. And as I have discussed earlier, the CMRR, which is nothing but common mode rejection ratio. Common mode rejection ratio. In fact, for better understanding, I am writing the definition. I am writing the definition of common mode rejection ratio. So the ability of op-amp, the ability of op-amp to reject the noise appears across the common input is known as the CMRR. So the ability of op-amp to reject the noise which appears across the common input is known as the CMRR. So for the ideal situation, we don't want any noise at the output. So mathematically, one can define CMRR will be equals to ratio of differential gain AD upon A. Now, in ideal situation, you can check ACM should be equals to 0. Means if VID is 0, if there is 0 input, then we can't expect any output from there. And differential gain AD, which will be very, very high. You have seen that it was somewhere infinite given in case of ideal situation, the differential gain. It is very, very high. So ideally, when we are putting this condition, 0 condition, that means my CMRR equals to somewhere AD divided by 0, which is nothing but infinite. And you can check, we have discussed this quantity while we are covering the characteristics of ideal operation amplifier. There is another unit. If we are representing CMRR in decibel, in dB, then it can be defined as 20 logarithmic of base 10 AD upon ACM. So this is the mathematical definition. Either we can define in terms of ratio. So this is the ratio of differential voltage gain to the common mode voltage gain, or it can be defined in decibel. So in practical situation, somewhere the value of CMRR is of level of 90 decibel. In practical situations, somewhere it has a value of 90 decibel. Is my slew rate, or in short, it is termed as SR. So let us first check the definition of slew rate. So it is the maximum rate at which, this is the maximum rate at which amplifier output changes in volts per microseconds. That means I can say that slew rate is change in output voltage V naught per change in time. SR will be equals to delta V naught divided by delta T. So its unit is volts, and we are interested to see this changes in per microseconds. Now let us check this parameter again for ideal op amp. For ideal op amp, you can see that if you can recall, we have discussed SR will be equals to infinity for ideal op amp. Now we have to determine this. What is this? Delta T. This is the change in time. So if we are giving if we are giving input at instant t1, suppose we are giving input as at instant t1, then ideally we don't want any delay. Ideally we want this delta t will be equals to 0. I want output at the same instant, at instant t1. I want v naught at this instant. So my SR will be equals to v naught divided by 0, that means equals to infinite. So this is an interesting parameter, slew rate, which is having a value infinite, or practically it should be very, very high. Practically this parameter should be very, very high. Now There is another interesting concept which is very important for further study, and its name is virtual ground concept. Virtual ground concept. Or there is a bit similarity between the two relations, virtual ground and virtual short. So, for better understanding, I'm drawing one diagram by which one can easily understand. If you can recall, this was the symbol of op-amp, inverting terminal, non-inverting terminal. I am saying that the two terminal voltages, this is V1 and this is V2. Differential input voltage is VD. So my differential input voltage VD will be equals to V1 minus V2. This is my differential input voltage. If you can see the internal structure, I have shown over there some input resistance. So this is my Ri, and I have shown over there an output resistance with some gain and measured with reference to ground. And we have marked this voltage gain AV multiplied by differential voltage gain VD, and this is my R naught. So this is the AC equivalent circuit we have discussed for practical case. Practical case AC equivalent circuit. However, in ideal situation, for ideal situation, Ri becomes infinite ohm and R naught becomes 0. Open circuit and R naught need to be short circuit. So if it is open circuit, you can check if it is open circuit Ri, that means no internal current can flow. That means I am saying that I equals to 0. I equals to 0 because current cannot flow through the open circuit. Current cannot flow through the open circuit. And if you can recall, we have discussed in the characteristics of ideal operation amplifier, that is my voltage gain AV equals to infinity. And from this particular term, if my output is V naught, then you can check my AV equals to what? Output voltage upon input voltage, and input voltage is my VD. So ultimately V naught divided by V1 minus V2. So this will be infinite. AV will be infinite. AB will be infinite if VD equals to 0. You can simply check the mathematics. V naught divided by 0 is infinite, and if VD differential input voltage is 0, this is indicating that V1 will be equals to V2. V1 will be equals to V2. So what is the meaning? If suppose I am connecting terminal V2 as ground, if V2 is grounded, then terminal V1 is virtually grounded. then terminal V1 is virtually grounded. So it seems like a virtual short is created between these two. Okay, having both are having a voltage and current value 0. That means V1 is grounded, that V2 is grounded, that means V2 equals to 0. As V2 is 0, therefore V1 will also be equals to 0. But over here you can check, V2 is actually grounded, V2 is actually grounded, but V1 is virtually grounded terminal. So this is the concept, virtual ground concept, and this concept is valid for ideal situations. That means this is valid for ideal op amp. This is very interesting relation. Probably in the next module, when we discuss different operations of operational amplifier, then we will use this concept for the detailed analysis. Thank you.